So today we have an interesting geometrical problem. We take a semicircle. Now we draw another semicircle so that the diameters of both of these semicircles are perpendicular to each other. Now we mark some of the points inside the diagram, like this point we take as A, this one as B and this one as C. Now we draw a line segment joining the points A and C. Now this particular line segment also passes through the intersection point between these two semicircles. Now talking about the size of these two semicircles, this particular semicircle is bigger in comparison with this semicircle, okay? Now we inscribe a pink circle inside the bigger semicircle in such a way that it is tangent to the yellow line segment. Also it is tangent to the diameter of the bigger semicircle, and also it is tangent to the smaller semicircle externally. Similarly, we inscribe a blue circle inside the smaller semicircle in such a way that it is tangent to the yellow line segment. Also it is tangent to the diameter of the smaller semicircle, and also it is tangent to the bigger semicircle externally. If we take the radius of the bigger semicircle as A and the radius of the smaller semicircle as equals to B, the question over here is to find area of the pink circle upon area of the blue circle in terms of A and B. So this is Anmol, and now let us see the solution. How can we find the value of this fraction in terms of A and B? Okay, now let us start with the solution. So first of all, let me tell you a thing, that the solution of this particular problem will be in two parts. In the first part, we will be playing around with the pink circle, and in the second part, we will be playing around with this blue circle. And from each of this part, at the conclusion, we will get equations, and comparing that equations at the end will give us the final answer. So let us start the solution by playing around with the pink circle. So we can clearly see that the pink circle is tangent at 3 points. This is the first tangent point, here is the second tangent point, and here is the third tangent point. So the third tangent point is between a circle and another circle, so that theorem we will utilize a bit later on. But before that, let us utilize this thing, that a circle is tangent to straight line. So when a circle is tangent to a straight line and we draw the radius for the circle to that tangent point, the angle formed over there would be 90 degrees. This is the very simple theorem. The angle formed at the point of contact between a radius and tangent line is always 90 degrees. And similarly for the other one, that is for this yellow line, here we draw the radius and this angle would be 90 degrees. Okay, so these two lines are ultimately the radius for this pink circle. Now what I will do is I will simply draw a straight line from this particular corner to the center of this circle. Now look carefully, this particular triangle and this particular triangle are congruent to each other because of right angle hypotenuse side. Here is the right angles, here is the common hypotenuse, and these two sides are equal because they are ultimately the radius for the pink circle. So as these two triangles are congruent, rest of the things between them become equal. This means the length from here to here would be equals to the length from here to here. Keep this thing as it is, we are going to utilize this thing a bit more later on. And now we are going to do the workings for this third tangent point, that is between two circles. So we all know this theorem very well, that is, if there are two circles that are tangent to each other either externally or either internally, in both the cases, if we draw a straight line joining the centers of these two circles, it will also pass to the tangent point. Either the case is internal or either the case is external. In both the cases, if we draw a straight line joining the centers, it will also pass to the tangent point, okay? So the same theorem can be utilized in our problem because we can see we have two circles that are tangent to each other. So now if I will draw a straight line joining the centers of these two circles, it will also pass through this tangent point, okay? And as this is a tangent point, both the circumference are touching to each other only once, not like this way. This means not two times, only one times, because they are tangent. And because of that, we can just do one more thing, and that is like this way. The distance from here to here is ultimately the radius of the pink circle, and let it be equals to a variable something x. So we are taking the radius of the pink circle, so let us write it down. So radius of the pink circle we have taken as a variable x, okay? And similarly, when we will move forward in the solution, we will take the radius of the blue circle as equals to y, okay? Here circle is remaining, so let us write down. So radius of the pink circle we have taken as x, and the radius of the blue circle when required we will take it as y, okay? So the length from here to here was just the radius of the pink circle, and that is having a length x, okay? Now the length from here to here is ultimately the radius of this semicircle. So now look carefully, the diameter for this semicircle was having a length b, therefore the radius of this semicircle would have a length b upon 2. So the length from here to here, that is the radius, would be b upon 2. again the length from here to here would be b upon 2, and similarly the line segment from here to here is ultimately the radius of this semicircle, hence it would have a length b upon 2. Now the complete length from here to here would simply become x plus b upon 2, and this is because these two circles were tangent to each other. Okay, so let's write down this thing. The complete length from the center of this circle to the center of that circle is having a length x plus b upon 2. Okay, so till now everything fine. Now what I will do is I will drop a perpendicular from the center of this pink circle to this particular line segment, that is ultimately the diameter for the smaller semicircle. So here we drop the perpendicular. Okay, now look carefully. In this particular quadrilateral, 3 of the angles are 90 degree, hence by angle sum property the fourth angle would also become 90. Now in a quadrilateral we have all the 4 angles as 90 degree, hence it becomes a rectangle. In rectangle, opposite sides are equal. Now look carefully, the length from here to here is ultimately the radius of the pink circle, hence it would have a length x. So if that length is equals to x, this length would also be equals to x, because we form this quadrilateral as a rectangle, so opposite sides become equal. Now the complete length from the center of this circle to this point was b upon 2. Some length in that we have got as x. Therefore the remaining length, that would simply be from the center of the semicircle to this point where we have dropped the perpendicular. So that length would be the longer minus the shorter. Hence this particular length would be b upon 2 minus x. Okay. Now look carefully, we have formed a right angle triangle over here. So in this right angle triangle we have the length of the hypotenuse, that is x plus b upon 2, and then we have the length of the height, that is b upon 2 minus x. So the right angle triangle that we have formed is somewhat like this way. So let us draw it down. So the right angle triangle is like this way. The length of the hypotenuse is b upon 2 plus x, and the length of the height is b upon 2 minus x. So now what I will do is I will simply apply the Pythagoras theorem in order to get the value of the base. So for now let the base be of length p. So now let us apply the Pythagoras theorem. So according to it, the base square plus the height square would be equals to the hypotenuse square. So b upon 2 plus x the whole square. So now simplifying this thing will give me p square plus b square upon 4 plus x square minus bx equals to b square upon 4 plus x square and plus bx. This and this got cancelled out from both of the side, and simplifying this thing at the end we will get the value of p as equals to square root of 2bx, and only the positive value because p is a length. So the length of p we have got as square root of 2bx. Now in this particular diagram the length p is from here to here, so let us mark it down. So the length p is from here to here. Okay, now what I will do is I will draw one more line segment. So now this time the line segment will run from the center of the pink circle, to this particular ending of the diameter. Okay, so from here to there we draw a straight line. Okay, now look carefully, we again have this bigger right angle triangle. Again this is the right angle for that triangle. The base of this right angle triangle is again p. Now what about the height of this right angle triangle? So ultimately the height of this right angle triangle is from here to here, so that complete length is b upon 2 plus b upon 2 minus x. So this time the right angle triangle that we have formed is like this, this and this. Okay, the length of the height is b upon 2 plus b upon 2 minus x, and the length of the base is ultimately p again. So now simplifying this thing will give me b minus x. So b minus x, and the value of p we have got in this equation, and that is square root of 2bx. So instead of p we will write square root of 2bx. Now in this particular triangle, if we apply the Pythagoras theorem, the length of the hypotenuse will turn out to be square root of b minus x the whole square plus 2bx, and this thing will simply give us square root of b square plus x square. So let us write down the final thing only. So the length of the hypotenuse for this right angle triangle we have got as square root of b square plus x square. Okay, so this was the second time we took a right angle triangle, and there's one more needed. So look carefully in the diagram. The line segment that we have previously drawn from the center of the pink circle to the end of this diameter, because of that we have formed two right angle triangles. One of the right angle triangle was this particular one that we have just utilized. Now let us utilize the second right angle triangle, that is this particular one. Okay, look carefully, this right angle triangle, the 90-degree angle is right over there. So now in this right angle triangle, this particular length is ultimately the radius of the pink circle, hence it would have a value x. Now look carefully, for this right angle triangle, again the hypotenuse is the same line segment, the line segment that we have drawn from the center of the pink circle to that end of the diameter, and the length for that line segment we have just found as square root of b square plus x square. So this time the right angle triangle that we have formed is like this way. Here we have the straight base, then we have the perpendicular, and then we have the hypotenuse. This particular line segment is the same line segment that was present as the hypotenuse for this right angle triangle. Okay, here we have the 90 degree, this length is x, and as these two line segments are the same line segments, therefore the length of this one would also be square root of b square plus x square. Now again we have a right angle triangle, the value of the hypotenuse is square root of b square plus x square, the value of the height is x. Therefore, by applying the Pythagoras theorem and doing some kind of simplifications, the value of the base will turn out to be simply b. So the length for the base of this particular right angle triangle is equals to b. Now look carefully in this particular diagram. The length that we have just found is ultimately from this perpendicular to this particular point, and that we have got as equals to b. Now recall that we have got this quadrilateral as rectangle. In rectangle, opposite sides are equal. So from that we have marked this length and this length equal. What about this length equals to this length? So the length of that line we have already taken as equals to p. So ultimately the length from here to here would also have a length p. Okay, the complete length from here to there was equals to a, some part we have got as p. Therefore the remaining part that is going to be from here to here we have already marked would be equals to a minus p. Now recall that we have got the value of p as equals to square root of 2bx. So instead of p we will write its value, and that is square root of 2bx. Okay, square root of 2bx. Now as we have got these two triangles congruent to each other, this length would be equals to that length. One of the length is already a minus the square root of 2bx. Therefore the length of this one would also be a minus square root of 2bx, and this length is from this corner to this perpendicular, and just a few minutes ago we have got the length from this perpendicular to that particular point. Hence the complete length from this point to that point can be calculated, and that would be simply the addition of these two. So the complete length from this point to that point is ultimately representing the length of the yellow line segment. So the length of the yellow line segment is ultimately equals to a minus the square root of 2bx added with b. The addition of these two simply gives us the complete length of the yellow line segment, and this thing would simply be equals to a plus b minus the square root of 2bx. And this is the first important equation, and here comes the end of the first part of the solution. Okay, now let us start with the second part of the solution, in which we are simply going to play around with the blue circle. For this blue circle, we will do the same things that we have done to the pink circle. So first of all, we will draw the radius to the tangent points that are between the circle and straight line, and therefore the angle form over there would be 90 degree. Again we have these two triangles congruent to each other, hence this length would be equals to this length, and we will utilize that thing later on. Now as this particular blue circle was tangent to this bigger semicircle, and according to the theorem that we just saw, if two circles are tangent to each other externally or internally, the centers of both of the circle and the tangent points are collinear. Hence if I will draw a straight line joining the center of these two circles, it will also pass to this tangent point. Okay. Now what I will do is I will simply drop a perpendicular from the center of this circle to the diameter of the bigger semicircle. And again we have this particular quadrilateral. Three of the angles are 90 degree, hence by angle sum property the fourth angle is 90 degree. The radius of this blue circle we have already taken as a variable y, hence the length from here to here would be equals to y. As this particular quadrilateral is a rectangle, the length from here to here would be equals to y. This is the center of the bigger semicircle. The diameter of the bigger semicircle was having a length a, hence the radius would have a length a upon 2. Therefore the length from here to here would be a upon 2. This much length we have got as y. Therefore the remaining length that is going to be from here to here would have a length a upon 2 minus y. Okay. Now look carefully. The length from here to here is the radius of the bigger semicircle, hence it would have a length a upon 2. The length from there to there is the radius of the blue circle having a length y, hence the complete length of the line segment that is joining the centers of these two circles would simply be a upon 2 plus y. Okay. So now here we have a right angle triangle. The hypotenuse is a upon 2 plus y. The base is a upon 2 minus y, hence the length of the height would simply be square root of 2ay. And again this is a rectangle, hence the opposite sides would be equal. So if this length is square root of 2ay, this length would also be square root of 2ay. Now the length square root of 2ay is from this particular point to this particular point. The complete length from that top point to here is ultimately the diameter for the smaller semicircle that was having a value b. Hence the remaining distance that is from here to this perpendicular would simply be the longer distance minus the shorter distance. So longer is b and the shorter one is square root of 2ay. Hence this remaining length would be b minus square root of 2ay. And as we have seen, these two triangles are congruent by right angle hypotenuse side. If this length is b minus square root of 2ay, the length from this perpendicular to that end point would also be b minus the square root of 2ay. Okay, now what we will do is we will draw a straight line from the center of this blue circle to this end point of the diameter. So a straight line from this point to the center of that circle. Now look carefully, we have again formed a right angle triangle like this way. Here is the right angle triangle. The height of this right angle triangle is square root of 2ay. Now what about the length of the base? So this much length we already have as a upon 2 minus y. Here is the center of the circle and here is the end of the diameter. Hence the length between these 2 points would be the radius of the bigger semicircle that was having a length a upon 2. And hence the complete length from here to here would be a upon 2 plus a upon 2 minus y, and that would simply result in a minus y. So the length from this point to this perpendicular is a minus y. Okay, so now for this bigger right angle triangle, the length of the base is a minus y. The length of the height is square root of 2ay. Therefore, by applying the Pythagoras theorem, the length of the hypotenuse that is going to be from this point to that point would simply be square root of a square plus y square. Okay, now look carefully in this right angle triangle. The height of this right angle triangle is this particular length, that is the radius of the blue circle, hence it would have a length y. The hypotenuse is having a length square root of a square plus y square. Therefore, by applying the Pythagoras theorem, the value of the base that is from this point to this perpendicular would simply turn out to be simply a. Okay, so now according to this thing, the complete length of the yellow line segment, so according to this second situation, the complete length of the yellow line segment we have got as b minus the square root of 2ay plus a. And this thing can also be written as a plus b minus the square root of 2ay. And this is the second important equation. Hence here comes the end of the second part of the solution. Now let us conclude the solution. So first of all, look carefully. From the first equation we have the length of the yellow line segment, and from the second equation also we have the length of the yellow line segment. Hence these equations can be simply compared. So from the first equation, the length of the yellow line segment is this thing, that is a plus b minus the square root of 2bx, and this thing equals to the length of the yellow line segment from the second equation, that is this thing, and that is a plus b minus the square root of 2ay. Okay, now a plus b from both of the sides can simply be cancelled out, and whatever is remaining we can simply square that thing. So we will get 2bx equals to 2ay. 2 and 2 can be cancelled out, and at the end the value of x upon y would turn out to be a upon b. Now what I will do is I will simply square both of the sides. So I will get x square upon y square equals to a square upon b square. Now in the left hand side what I will do is I will simply multiply and divide pi. Okay, so now the left hand side looks like pi x square upon pi y square, and this thing equals to a square upon b square. Now recall that we have taken x as the radius of the pink circle. So if the radius of the pink circle was equals to x, area of the pink circle would turn out to be pi x square. And if the radius of the blue circle was taken as y, area of the blue circle would turn out to be pi y square. And hence we have got the value of area of pink circle upon area of blue circle as equals to a square upon b square, and it is completely in terms of a and b, that were the diameter of the two semicircles. And hence this is the answer that we were looking for. So this was my way to solve this particular problem. If you have any other method other than this, do comment below, and if it's hard to comment you can email me, or else you can send it to me on my Instagram. The link is in the description.